This topic will discuss the theory for a fastener under fatigue analysis, subject to tensile loading. So mainly one thing you have to keep in mind that your problem is probably going to look like this because it's always preloaded, right? So you're going to have P minimum and you will have a P maximum. And I will tell you in a minute how we use these loads. But before we start the problem, as standard, just multiply your design factor for your P max, and then your P max, and then also multiply the design factor for your P minimum. Remember, we do not apply the design factor to this. So this is no ND. The first thing you want to check is fatigue resistance. So most likely, if it meets this criteria, it will be safe. So this is one of the first criteria that you check. And remember, this comes from your tables. And then the other thing you need in a problem is your endurance limit. If you go to table 8.17, you can find these endurance limits for various a sample of materials for bolts, and gives you the sizes of these bolts. And depending on the size, then you can go ahead and you can choose your endurance limits. However, I should warn you, although it says that this is fully corrected, what it does not include, it does include surface condition, includes the sizing. It does not include here temperature and reliability. So the temperature is a concern, or the percentage of reliability you want to add to the problem is a concern that needs to be added. Now, what do we do in the case in which we do not have this table? Well, most of these are typically steel, right? And we know that steel is typically 0.5 times SC prime. Okay, and this was given, if you go back to your notes from fatigue, we gave you the values for that. And in that particular case, then I'm so sorry, as you need to check the value that goes there. I think it's this. But then what you will do is you can find this multiply K infinite times SE prime. And one thing I want to point out here that I include KF in the stresses. I do not include it here. So we will stick with that methodology as we have been doing throughout the course. If we did that, then you can find the surface factor. Remember, this is a screw, and this is machined. All the screws are machined out. So this is the case that you will use for a bolt and for a screw, for a bolt, um, a fastener. This is what you will be using because it is machined. Okay. The surface factor, you will put this equal to 0. If you're actually calculating this, then this will be 0.85 because it's axial load mainly. This is your KD, your temperature effects if we needed to use them. This all depends on the temperature that you're using. This is the percent of reliability that you're talking about. So then from here, you will have this other factor. And then you can have other miscellaneous factors as well, right? So the same thing as we did before. Second thing we want to do is we want to find the alternate and mean loads. And to do that, we're going to have the following equation. Just give me a minute. Where this is what the equation is going to look like for alternating and your mean load that we'll use for analysis. And these values of your B as in bolt, okay, and minimum as in bolt. So this is actually given by this equation right here, okay? So this is minimum, this is maximum. In many cases, what we do is we actually repeat the load. So you take it to 0, we go back up, we take it to 0, we take it back up. So this is a load P. So you can see that actually starts at 0. So then in that case, your P minimum will be 0, but you do have a preload. So this is the load for P. However, the load for F that we will be using in the problem will actually look something like this because it does have a preload. Okay, just want to point this out because that's important. Then when you're doing the alternating mean and axial stresses, they're given by this equation. Remember, this comes from tables. This we just calculated. This is the joint stiffness constant, and then this is how you calculate this. Just note that only the mean has this term. This one doesn't have these terms here because they cancel out. Okay. Um, then you want to find this factor. To find your KF, we're just going to be conservative and assume that you can apply it all the way across, both for mean and alternate. Another method could be to use the method where your the notch cannot be avoided, so then you can approximate this using some of the Dolling's method. However, we are not going to do that here. Okay, your book doesn't do it, and we are not going to do it. So these values actually come from this table, and if you don't have anything, these are typically what we work here. Most of the problems will be cut threads. If nothing is given, then just assume cut threads is common. Just assume this or you can assume this. But typically, this is good for power screws. This is a good approximation for power screws. However, for fasteners, this is a better approximation, okay? Because they don't have fillets, they actually cut threads. And then, so this will be for fasteners. And again, this is typical, okay? This is what, it can have different values also. If not, then you can always use the other method of going to the table A15, and like we did in the for the power screws as well, and then use the fillet value. That's also good approximation. Then once I have that, then my big S and big M is equal to this. And then from here, I find my S maximum. First, you want to make sure a static check at the maximum loads. That this is divide. Now remember, I'm doing proof load, okay? Proof stress, not yield stress. And that has to be bigger than 1. Then I move on and I calculate my Goodman theory equivalent stress. This is my Goodman stress. Do your check. If it's bigger or equal than 1, then we're good. You're ensuring that there will be no yielding will ever take place. And then for infinite life, then you use the same method that we discussed in the previous chapter, in the previous lectures as well. Now, you always want to design for infinite life. If that was not able to achieve, you could do a couple of things. You could change the joint thickness. You could change the material, the bolt grade, the size of the bolt. I always recommend avoid making the size of the bolt bigger if you have the other options. Why? Because making the size bigger, that will actually increase the thickness of your main structure and of your members, and that's adds weight to your structure, which you probably don't want to do that. That's extra material. However, doesn't matter what we do, we just want to make sure this is always satisfied in the problem. Okay, so basically this concludes our topic on how to do fatigue analysis. The next lecture will be an example.